Okay, can somebody confirm you can hear me?
Yeah, I can hear you.
Great. Before we begin, are there any questions? All right, let's begin. Oh, wait a minute. Let me activate my share my screen. There, you should be able to see my screen now. So today is October 3rd, and we should be discussing uh, Chapter 2, Chemical Principles. Hopefully you did the practice quiz. Let me check on that. I think if you didn't do the practice quiz, I think I allow you to still do it, but it was supposed to be done Wednesday. Close that. Normally, I cut off the quiz exactly when the deadline is, but this is the practice quiz, so I think I've got it like a day later. Please take the practice quiz because it'll ensure that you have Respondus Lockdown Browser working on your system. Yes, you can take it till 11:59 p.m. Tonight. I do give you extra credit on this quiz. It's worth 1 point of extra credit. And each question will be point 0.1 per point, point 0.1 point. So 0.1 point if you get it correct. Any questions about any of that? If you do not get the lockdown browser to work on your system, you should contact the computer help desk. They're experts at getting it to work on your system. Most likely, all you need to do is change a setting on your computer to get the lockdown browser to work. Any
Um,
questions?
I had a question. So in the description, it says that we should also take the practice quiz 1A. I wasn't able to find that.
That there is no quiz 1A. Let me change that. Sorry, this is a whoops, where is that? A I just rolled over the class from last fall and I've changed it. I think I changed it last winter, so it's been a long time ago, but there is no practice quiz 1A. This quiz has multiple choice questions. There was too much cheating on the essay questions, so I gave up on them. Any question about anything? All right, that's corrected. So hopefully next fall it'll be correct. Sorry about that. Um, hopefully, hopefully there's no other. But if you see a concern like that, let me know. I didn't remember that was in there, and I just updated the class and didn't change that wording. All right. We will be having a lab today. So let's go on to chapter 2. Here it is. So I have that we had talked about water being a good solvent, and that's because it can dissolve any polar molecule or any ionic molecule. Water is a good solvent. Polar molecules are hydrophilic. What does that mean? It means that they are attracted to water. Literally, this means water, hydro, and then philic, lover. But what we mean by hydrophilic means that they are attracted to water and will dissolve in water. Nonpolar molecules are repelled by water, and we say they're hydrophobic. Literally, this means fear of water. Obviously, something that's hydrophobic doesn't fear water, it just doesn't dissolve in it. An example of a hydrophobic molecule is oil. As you know, when you make salad dressing and you shake it up, the oil molecules will separate from the water and vinegar, and the oil will come on top, and then the vinegar will be down below. Any questions about any of that? So fats and oils are generally hydrophobic. Water, most carbohydrates, certainly glucose and fructose. Amino acids are all hydrophilic. Well, I shouldn't say amino acids because they're both hydrophilic and hydrophobic. We'll talk about that when we talk about proteins, but what would be another example? Uh, Nucleotides are hydrophilic. Water has a chemical covalent bond within the water molecule. And then in liquid form, it has hydrogen bonds between water molecules. Hydrogen bonding between water makes water excellent at buffering the temperature. You should know this because most of you live in Western Oregon or Western Washington, and our temperature is buffered by the Pacific Ocean. And it's simply because water is excellent at buffering the temperature. And the reason why it's so good at buffering the temperature is that it has two things that can absorb the energy of heat when we apply it to the water. The water absorbs a lot of heat before it evaporates. It takes energy to break the hydrogen bonds between the water molecules. And this is one thing that can absorb the energy when you apply it to water, meaning the hydrogen bonds can absorb that energy. And if you get enough energy, you will break the hydrogen bonds between that water molecule and the other water molecules, and then that water molecule will evaporate. And that's one reason why water is such a good cooling, like when we perspire, and that is the hottest water molecules are the water molecules that leave the water. The cooler water molecules, which have some or all of their hydrogen bonds, will not leave the water. Only the hottest water molecules will leave the water. Any question about any of that? Okay, the second thing that water molecules have to absorb the energy when you apply energy to water is the water molecule itself can absorb that energy. And when it absorbs that energy, the water molecule will move around and vibrate more. And that is literally the measure of the temperature, how fast the molecules are moving. That is what we mean by temperature. So when we add heat to something, the temperature will elevate, and that's because the molecules are moving around and vibrating more. Any question about any of that? So water has two things that can absorb energy. I thought I had that in another slide here. I'm not seeing it. Water has two things that can absorb energy, and that is the water molecule itself, in which case it will raise the temperature of the water because the water molecules are moving around with more energy, meaning they're moving around more, just moving faster and vibrating faster. And that will raise the temperature of the water. But also the hydrogen bonds can absorb the energy. And if they absorb enough energy, all of the hydrogen bonds will break, and then that water molecule will evaporate. Any question about any of that? Now, do you know another substance that can absorb energy in two ways? Both by elevating the temperature, meaning the molecules are moving around faster, and by breaking hydrogen bonds. Can you think of anything else? Nobody's coming up with an answer, and that's because there aren't that many other things that have two ways to absorb energy. Like when we apply energy to heat or to fat, only the molecules themselves can absorb that energy. And then that will raise the temperature of the oil or the fat. And that means when you apply the same amount of energy to the same amount, meaning the same, let's say 100 grams of water and 100 grams of oil, the oil will raise in temperature higher than the water. And once again, that comes back to water is excellent at buffering the temperature. Any question about any of that? All right. Water can be split. And on the planet Earth, when H2O breaks apart, it will split into H plus and OH minus. This is on the planet Earth, not the surface of the sun. On the surface of the sun, H2O can break into hydrogen ions and oxygen ions. That doesn't happen normally on the planet Earth. Now, it could happen if you were to submit electricity to water and have electrolysis, but that's pretty unusual circumstance. Normally, water, when it splits apart on the planet Earth, only splits, I'm talking about liquid water, by the way, only splits into H plus ion and OH minus. Remember, H plus ion is a proton, and then OH minus, we have a name for that, the hydroxide ion. The charged molecules, meaning the H plus and the OH minus, participate in chemical reactions of the water, and they give the water its pH. Any question about any of that? All right. pH is a scale of the measure of hydrogen ions in concentration in the water. Let me blow this up so it's a little easier to view. The pH scale, I can't get that out of the way here. All right, let's put it down here, and you're sort of blocked there, but well, that's not too much of a block. The pH scale runs from 0 to pH 14. At pH 0, all of the water molecules have broken apart into hydrogen ions and OH minus, and obviously something has to absorb the OH minus or else it wouldn't be a pH 0. We'll skip that for the moment. The point is that all the water molecules are broken and then the apart, and then there's H plus in solution. How could you ever have water with all of the water molecules H plus? I don't know, but that's just what the pH scale is, okay? Any question about that? Sorry, I just asked myself a really difficult question. I don't know the answer to it. Um, but pH 1 we can talk about. That would be the pH uh, the car battery acid, which for us will be the most acidic thing you could think of. It's even more acidic than stomach acid. Stomach acid is between pH 2 and pH 1, but car battery acid would be pH 1. Any question about any of that? So when water first breaks apart, meaning H2O breaks into H plus and OH minus, uh, that will be pure water, where the H plus ions in concentration will be equal to the OH minus in concentration. Pure water, pH 7. Any question about any of that? So at pH 7, the H plus ions equal the OH minus ions. And then when the H plus ions are more numerous than the OH minus ions, we have increasing acidity. Urine around pH 6, tomato juice and wine around pH 4, grapefruit juice around pH 3, lemon juice around pH 2, stomach acid around between pH 2 and pH 1.5. Any question about any of that? Meaning increasing H plus ions in solution. Now, you can have the H plus ions in less concentration than the OH minus ions, and this we have increasing base, basicness or basicity or alkalinity. There's the word I can say. Increasing alkalinity, where the OH minus concentration increases over that of the H plus ions. Human blood is slightly alkaline between pH 7.4 and 7.2. Seawater a little bit higher than pH 8. I don't remember exactly what seawater is. It used to be 8.2, but I think it's 8.3 or 8.4 now. No, it used to be 8.4, 8.3, and now it's 8.2. Is that right? Yeah, because of increasing carbon dioxide in the atmosphere. Um, Milk of magnesia around pH 10.5. Household ammonia around 11.5. Household bleach around pH 12.5. And let's see if I got this, move this out of the way. I don't think you know, well, you probably know oven cleaner is around pH 3.5. Lime water is higher than that, close to pH 14. So as you increase the pH number, you increase the OH minus in concentration. So the OH minus is more numerous than the H plus ions. Any question about any of that? Okay, an acid is a substance that dissociates in water and gives up one or more H plus ions. HCl is an acid because inside liquid water, HCl will break apart into H plus ions and Cl minus. And then the H plus ions will increase in concentration, making the water acidic. Any question about any of that? Now, your textbook says that a base is a substance that dissociates in water and gives up OH minus, like sodium hydroxide in water will break apart into sodium plus 1, and OH minus 1, which is increasing the OH in concentration. So sodium hydroxide is a base. Any question about any of that? Well, I'm going to tell you the textbook is slightly wrong, and that is a base is a substance that either gives off OH minus or absorbs H plus in solution. Like when we have bicarbonate, and that would be like baking soda, sodium bicarbonate, and you put it in water, this right here can absorb H plus in water, forming carbonic acid, H2CO3, that will absorb the H plus and the water, making the solution slightly basic. Any question about any of that? So a base is a substance that either gives off OH or absorbs H plus ions in solution. A salt is any substance that dissociates into a cation and an anion, neither of which are H plus or OH minus. So sodium chloride is a salt, and everybody knows that because sodium chloride is table salt, will dissociate into a cation, sodium plus 1, and an anion, chloride minus 1. However, magnesium chloride, which is not table salt, can dissociate into a cation, magnesium 2 plus, or plus 2, whichever way you want to word it, and 2 chloride minus 1s. So magnesium chloride is also a salt. So in chemistry, a salt literally means any substance that can dissociate into a cation and an anion. Electrolytes are substances that can dissociate in water and then allow electricity to travel through the water. Like sodium chloride is an electrolyte because it'll break into a cation and an anion, which can then transmit the electrons or the electricity through the water. And if you do not know, you should avoid being in the ocean or any salt water during a lightning storm, because if lightning hits the water will transmit the electricity of the lightning strike very well, meaning a long distance. So you should get out of the water if it's salt water. On the other hand, if you're in a pool of fresh water is not an electrolyte and it does not conduct electricity well. And so to get a shock from a lightning strike, the lightning strike has to be really close to you, within a few feet. Any question about any of that? Which I suppose a pool is usually not that big, so if it hits the pool, and most pools, you would be in trouble, but if it hits a large pool and you're on the other side of the pool, you would be okay. Any questions about any of that? All right. So an electrolyte is any substance that can conduct electricity, and all salts are electrolytes because all salts can conduct electricity. So let's return to the acid-base balance. Organisms need to maintain a fairly constant balance of cellular acids and bases to remain healthy. In Biology 160, that was called homeostasis. And we're not going to talk about homeostasis here, but you do need to retain your maintain your acid-base balance to remain healthy. And how we do that is our blood has molecules in it that are buffers. One of the main one is H. Oops, not doing that here. Let's go sodium bicarbonate. I got to blow this up so you can see it. Oop. I probably can't make that a superscript. No, I'll just make this smaller. That looks close to a superscript. What size was that? Well, we'll just copy that. You know, that's not quite right. Although it is partly right. Let me just copy this right here. H2. Oop. Why didn't that do that? All right. Can split into H plus plus HCO03. That here. And if need be, this HCO3 can, let's put that here, can split I probably can't do that. That should have a -2 charge on it, and I'm not sure how to get that up here, so I'm not even going to try. Wait a minute, this should have a -1, sorry. This should have a -2 charge on it, and I don't think I'll be able to put it up there as a -2. The point is we have this in our blood, which can release hydrogen ions and make this, which can buffer out the OH minus in our blood when we get too much of it. And if need be, this doesn't happen because this happens at a lower pH than our blood would get. The HCO3 can actually split into H plus and then CO3 with a -2. That doesn't happen in our blood because we'd be sick or you'd die if that were to happen. And then the reverse can happen. We can have this if we have too much acid in our, oop, too much acid in our blood. We can absorb the acid by binding to this, forming this. And then this can be transported to the lungs where we will breathe it out as CO2. Let me get that again. This only happens in the lungs where H2CO3 um, breaks into CO2, H2O. Oop. Plus CO2. And then you breathe out the CO2. Oh, that worked that time. Any question about any of that? That should be a H plus superscript, which I can't do, so I'm just going to erase it. Anyways, we have H2CO3 and HCO3 in our blood, which helps buffer the pH of the blood. And that's why if you chug Coke, which is acidic, you don't get sick and then die from chugging the Coke. It's because we have buffers in our blood. Any question about any of that? All right, getting back to acid and bases, I mentioned that the pH is the amount of hydrogen in solution. The pH is literally equal to the negative log of the concentration of H plus ions in solution. pH scale being between 0 and 14. And it's a log scale, that's why it's log here. Increasing H plus ion increases the acidity. Decreasing H plus ions in solution increases the alkalinity, meaning the pH raises above pH 7. Acid solutions have more H plus ions in solution than OH minus. Basic solutions have more OH minus in solution than H plus. Most organisms grow best between pH 6 and pH 8, meaning most organisms grow best around pH 7. Any question about any of that? All right. Let's talk a little bit about organic chemical compounds. Here you're seeing organic chemical compounds. You note that they are generally bigger and more complex than an inorganic compound. Even acetic acid, one of the smallest organic compounds, is more complex than an inorganic molecule like CO2. Many of the organic compounds are like this one, where you see many atoms attached, and most of those attachments are carbon-carbon attachment, meaning the carbon-carbon bond is making most of the molecule. The hydrogen is being attached to the carbon, and then the carbon is held together by carbon-carbon bonds. There is an exception, like right here. Come on, mouse. We have this carbon bound to that carbon through an oxygen. So there are exceptions, but most of the bonds are carbon to carbon. Do not memorize these organic chemical compounds because you don't need to, but we have different organic chemical compounds, the simplest of which are called hydrocarbons, and all they have is carbon and hydrogen. Why didn't that go? There it is. So these are all hydrocarbons, methane, ethane, propane. They're the simplest. In fact, methane is the simplest organic compound. And all they have are carbon and hydrogen. You can have hydrocarbons in a ring structure such as this or this, in which case wherever there's a carbon, you have a point. So right there, right there, right there, that's all carbon. Or you can draw it out in the stick form like this, although that would be difficult to do in the stick form, but you can do it. So all organic compounds have hydrogen and carbon, obviously. Many organic compounds also contain oxygen, like acetic acid and whatever this molecule is here, phospholipid, has oxygen. They don't have much oxygen. This has two, this only has three, and then this one has many carbon bonds. I don't know how many, but probably over 20. You can count it if you want. Carbon bonds here, carbon bonds here, carbon bonds there. So organic chemical compounds have carbon and hydrogen. Many also contain oxygen, like amino acid, carbohydrate, nucleotides, lipids, various hydrocarbons. They all contain oxygen. Not very much. Some organic compounds also contain other elements like nitrogen, sulfur, phosphorus, and all of them are held pretty much together by carbon, covalently bound one molecule to the next. And if it isn't carbon, it will be a covalent chemical bond between one of these other molecules. Like right here, we have carbon, carbon, but right there we have carbon, oxygen, and then oxygen, carbon. But that's a chemically covalent bond holding the organic compound together. Compared to inorganic molecules, uh, organic compounds tend to be more complex. They also tend to be capable of more complicated biological functions. Some examples of organic chemical compounds include amino acids, carbohydrates, nucleotides, lipids, various hydrocarbons. Carbon is important in an organic chemical compound because carbon can bind to four different atoms, meaning four other atoms. Like this carbon here is bound to three hydrogens and an OH group. This carbon here is bound to three hydrogens and another carbon. Carbon atoms are often found bounded together in a chain or a ring structure, holding the molecule together. Like right here, isopropanol is held together by the carbon-carbon bonds. So we say that carbon is the skeleton or the backbone of most organic chemical compounds. In fact, I'm pretty sure it's almost all of them. It's just that you can have other bonds in the molecule as well as carbon-carbon. Like right here, we have oxygen. In the organic chemical compound, we have functional groups which bind to a carbon, and they influence the chemical behavior of the organic compound. To show you, methanol has a functional group OH on it, which then differs from methane, which only has hydrogen on the carbon. And the OH group gives the molecule methanol different properties than methane, which is carbon 4, CH4. Some different properties of methane is methane can dissolve in water because of this OH group. Methane cannot dissolve in water. Methane is hydrophobic. And methanol is hydrophilic. So the functional groups bind to a carbon and influence the chemical behavior of organic compounds. So functional groups are responsible for most of the chemical and physical properties of a particular organic compound. OH group, the hydroxyl group, in alcohols is hydrophilic, so it attracts water molecules to it and helps the molecule dissolve in water, but it can also dissolve in alcohol, which methane cannot dissolve in water. I don't know if it can dissolve in alcohol. It probably can because alcohol is both hydrophilic and hydrophobic, meaning alcohol can dissolve in lipids and it can dissolve in water. Any question about any of that? All right, so let's talk about the functional groups. OH is the first functional group, which we already talked about, which you find in alcohol. You can find that in various carbohydrates like fructose, or in lipids, or nucleic acids. So OH is a common functional group. And the R is just whatever the OH group attaches to. So the R simply stands for a rest of the organic molecule. Another functional group that you must know is NH2. This is the amino group, which is found in proteins and in amino acids. So NH2 is the amino group, and it binds to a central carbon. Let's move on. Another functional group you need to know is carboxyl group, and that is COOH, where that first O has a double chemical bond, covalent chemical bond, holding to the C, but the OH group only has a single covalent bond between the OH and the C. Carboxyl groups are found in proteins, amino acids, and lipids. Phosphate is PO4 with a negative charge. You find phosphate groups in ATP, DNA, and then in one lipid, the phospholipid. Why do I want you to be familiar with these groups shown in red, these functional groups? Anyone? Has to do with over here. All right, I want you to be familiar with these groups because they're the groups important in the biological molecules, meaning the molecules of life. Oh, where are we? Here we are. You should realize that frequently more than one functional group can be found in a single molecule. For example, amino acids have both the amino group and the carboxyl group. Any question about any of that? Is anyone there? Yep. All right. Organic compounds are can be made up of different units, which we call small organic molecules, and they can combine into a larger organic molecule that we can call a macromolecule. Macromolecules are also called polymers, consisting of many of the small repeating molecules, and they are called monomers. So, for example, starch is a macromolecule that we also call a polymer. Poly means many, and I don't remember what mer means, but many units making up the starch. And with starch, the monomer that it's made up from is many units of glucose. Any question about any of that? So starch, which is a large carbohydrate, is a polymer made up of many monomers, and the monomer is specifically glucose. All right, biological molecules or organic chemical compounds can combine where you have one monomer, ROH, and then RH can condense or undergo dehydration synthesis or condensation to combine this R here with that R, and then the H pulls off, the OH pulls off, and then they reform water. So a monomer and a monomer can combine to make well, this really would be a dimer here, not a polymer, plus water. And that's dehydration synthesis, where you're making a larger molecule than you're starting with. It's also called condensation reaction because water forms, water condenses. You can go the reverse, where you have a dimer, or in this case, a polymer, and water can come in. The water splits apart. One R gains an H from the water. The second R gains an OH from the water. And this is called hydrolysis. And an R stands for just some organic chemical compound. Like if R stands for glucose here, and well, let's say glucose here and fructose here, they could then combine to make sucrose, which would be RR. Two molecules of sugars, one glucose, one fructose, making sucrose, and then water will form. And then you can do the reverse, take the sucrose, add water to it, undergo hydrolysis, and then you gain your monomers back. Any question about any of that? Oh, hydrolysis. I was trying to remember. I wanted to say one other thing. Should be familiar to you if you watch, I think it's Back to the Future too. And that is when Marty McFly says to his mother, "Ma, you sure know how to hydrate a pizza." She was hydrating this black hockey puck that she put in her pizza machine and hydrated it, changing the black hickey puck into this beautiful pizza that came out of the hydrolysis machine. So hydrolysis should be familiar to you if you watch Back to the Future. Any question about any of that? All right, another example of dehydration synthesis or condensation reaction, where we have a monomer joining a polymer here, and the H comes off the polymer, the OH comes off the monomer, and then the R of this monomer will bind to the R of that polymer, making a larger polymer, and then water is formed as well. Hydrolysis, on the other hand, is adding water to a polymer. Water will then split apart, break this chemical bond there, and H plus from the water will combine and become an H with the polymer here, or the smaller polymer here. And then the other OH group of the water will break off and join the monomer. And then that will be a monomer, such as if this was starch, you can bring in water to break it into a smaller starch molecule, and then you'll make glucose there. Any question about any of that? So you should note the hydrolysis and condensation are the reverse of each other. So carbohydrates include sugar, starch, and other complex carbohydrates. They are important as an energy source for organisms, but they're also important for structure, like in a cell structure or in an organism, and they are important in nucleic acids. So carbohydrates are important in nucleic acids. They are not specifically used or specifically part of the nucleic acid, but well, that's not entirely true either. Ribose is found in the nucleic acid, so we'll just leave it at that. So they are part of the structure of nucleic acids. Carbohydrates consist of carbon, hydrogen, and oxygen, but they're more than just carbon, hydrogen, and oxygen. They exist in the general formula. For every one carbon, there's two hydrogen and one oxygen. So you can just repeat CH2O to the nth times for the carbohydrate. So for example, glucose is CH2O parentheses, and then the N will be 6. Meaning glucose is C6H12O6. So simple sugars and strings of simple sugars linked together are carbohydrates. And we can classify carbohydrates into three major groups based on their size. The smallest group are the monosaccharides. These are the monomers. A simple sugar, like glucose or fructose, is a monosaccharide. A disaccharide is two sugars chemically bounded together by a chemical covalent bond. And you can combine the monosaccharides of fructose and sucrose to make the disaccharide of, did I say that wrong? The monosaccharides of fructose and glucose to make the disaccharide of sucrose. And then the third carbohydrate is a polysaccharide. Poly means many, saccharide is a sugar group, so it simply means many sugar groups. And starch is a polysaccharide. Any question about any of that? All right, let's talk about the carbohydrates, the mono and disaccharides. Monosaccharides are simple sugars. They all contain 3 to 7 carbon atoms. However, most monosaccharides contain either 5 or 6 carbon atoms. Monosaccharides are sweet and they're water soluble, meaning they are hydrophilic. Disaccharides are formed by joining two monosaccharides in a dihydration synthesis reaction. And I've already stated this. You can combine glucose right here with fructose right there. The H comes off of fructose, the OH off of glucose to form water. And then this carbon here combined directly to this oxygen there to make the disaccharide sucrose. Any question about any of that? And then you can take disaccharide sucrose, add water. Water will split this chemical bond here. The H will go to the fructose, the OH will go to glucose, and then we'll have our two monosaccharides, glucose and fructose, which is made after splitting sucrose. Any question about any of that? All right, here's talking a little bit about the polysaccharides that consist of many saccharides, many monosaccharides. They are straight or branch chains. Starch is an example of a polysaccharide. Starch is mostly a straight chain containing glucose held together one after the other. Glycogen is similar to starch. It's just that glycogen is uh, a glucose chain that branches. And I should say it branches much more often than starch branches. So starch is mostly, not entirely, but mostly a single, composed of single chains of glucose held together, one after the other, in a non-branching chain. Mostly, obviously, there are some branching chain, but much less branching in starch than in glycogen. Glycogen, all of the molecules of the glycogen, meaning the carbohydrate, will branch. Some other examples, dextran, cellulose. And then here's a picture of some starchy foods. I think everybody knows bread, cereals, pasta, rice, and potatoes are starchy foods because they have a lot of starch in them. You should know that from potato starch and corn starch. I've never heard of rice starch, but I imagine that's possible. You probably don't know it, but beans and chestnuts are also good sources of carbohydrates. And that's because beans are about 1/3 carbohydrate, 1/3 protein, and 1/3 lipid. That's why beans are a rich source of starch. Chestnuts, I don't know the chemical makeup, but starch is a main portion of the chestnut. I'm sure chestnuts have some protein and I'm sure they have some lipid, but I don't know what the proportions are. Any question about any of this? All right, so this is showing you the slide of starch, mostly a non-branching chain. It does have a few branches on some molecules. Glycogen, similar carbon held together, glucose to glucose. But the glycogen will be a branching chain. If you don't know, glycogen is the way animals store glucose or carbohydrate. Your liver and then your muscle cells store glycogen. And then when you need glucose in your blood, the glycogen is split off to release glucose into the blood by the liver, meaning the liver does that. Cellulose, let me blow this up way, way big. Can't blow it up any bigger. So I blow up here. There, I can barely see it now. Cellulose is hooked together in a chain of glucose held together one after the other. It is true that this glucose has a different bond. You don't need to know that, but uh, why cellulose is so difficult to digest is not because of the chemical covalent bond holding the molecule glucose, not glucose, cellulose together. It's because besides that chemical bond, we have a lot of hydrogen bonds in cellulose, meaning here's that one chain of the monomers held together in cellulose. There's another chain, and they will hydrogen bond between each other. And cellulose has a lot of hydrogen bonds between their molecules. And that's why cellulose is so hard to digest. Humans can't digest it at all. Cows don't either. When the cow eats the cellulose in grass, it has it in the stomach, one of the four stomachs, and got four stomachs to retain the food longer so the cow can have ample time for digesting it. And what the cow does is it gives the cellulose to a protus in its stomach, and then the protus gives the cellulose to a bacteria in its gut to digest the cellulose. So neither the cow nor the protus, and I used to know the name of this protus, but I've forgotten, can digest cellulose. It's actually the bacteria in the gut of the protus that is digesting the cellulose. And the bacteria share the glucose that are released from cellulose with the uh, the protus, and then the protus shares the glucose which has been released to it with the host that the protus is in, which in this case would be the cow, meaning the cow does get some of the sugar when the cellulose is digested by the bacteria in the protus, which is in the stomach of the cow. Any question about any of that? All right, we'll talk about peptidoglycan later, so I'm not going to talk about it now. Shrink that down. And I'm not going to talk about chitin at all, but those are two other um, complex carbohydrates. All right, any question about the carbohydrates? If not, let's talk about the lipids. Lipids consist of carbon, hydrogen, and oxygen. However, lipids are mostly carbon and hydrogen. They do contain oxygen, but only at very low numbers. Lipids, for the most part, are nonpolar and insoluble in water, meaning a lipid is hydrophobic. There is one exception, and we will talk about that exception in a little bit, and that is the phospholipid is a lipid which does not fall into the category of nonpolar or polar. Most molecules can be discussed as either polar or nonpolar. Not all molecules, but many molecules. Lipids are important structural and energy storage molecules in animals and plants. Lipids are a primary component of the cell membrane, so you need lipids in your diet to make your cell membranes as well as structural and parts of your cell and energy storage roles. Let me see if this is or talk about that, or that's next? I think I will talk about it here. And that is lipids contain the most energy of any molecule per weight, meaning 1 gram of lipids contains more energy, meaning you'll get more calories from eating 1 gram of lipid than you will 1 gram of any other molecule. So if you were stranded in Point Barrow, Alaska in the wintertime and your car broke down and you have to hike 20 miles in the frigid weather to Point Barrow, Alaska, it would be good to carry as much lipids or fats as you can so that you could eat it and generate energy to help keep yourself warm and alive. It's just that lipids contain more calories, more energy than any other food that we can eat. More energy than carbohydrates, more energy than protein. It doesn't mean that lipids are good in your diet. All I'm stating is we do need some lipids, and it's best not to eat a lot in 1 week. Although this might be just old data. And the reason why I'm saying it's best not to eat a lot in 1 week is lipids are loaded with cholesterol, including the bad cholesterol. So if you eat a lot of eggs, you should probably get your cholesterol checked because you might be high on cholesterol. So once again, the point being that lipids consist of carbon, hydrogen, and oxygen. They are, for the most part, nonpolar and insoluble in water. Fatty acids are a major component of many lipids. They consist of chains of carbon. They do contain a carboxyl group, COOH, at one end. Most other locations of the fatty acid are simply hydrogen and carbon. Let me show that on the next slide here. Blow this up a little. Well, actually, let's go here. Oh, there, I can blow it up. So there is a fatty acid, does contain COOH, but all the other portions of the molecule are carbon and hydrogen. The fatty acids can be either saturated or unsaturated. A saturated fatty acid, see if I can move this slightly. A saturated fatty acid is a fatty acid that has a single carbon bond in all of the molecule. Wherever carbon is bound to carbon, saturated fatty acid will have only a single chemical bond between the carbons. On the other hand, an unsaturated fatty acid has at least one double carbon bond in the molecule. So here we're looking at let me blow this up. Fatty acid right here, another one right here, and both of these are saturated fatty acids because they only have single carbon bonds. But this one here has one double carbon bond right here, and this is an unsaturated fatty acid. You only need one to make it unsaturated. You can note that wherever you have a double carbon bond, that you put a kink in the molecule. It is thought, by the way, that that kink is what makes unsaturated fatty acids healthier for you than a saturated fatty acid. Meaning this molecule, because it has one double carbon bond, cannot come together and complex with other molecules like this very easily, because this tends to keep them from, I don't know, joining and forming a complex of many molecules held together. Whereas if you only have a saturated fatty acid, like if you were to have this right here with three saturated fatty acids instead of two, meaning this would not be a double carbon bond, it would be a single carbon bond. It wouldn't have a kink here, this would go straight out. Then this molecule can combine with other saturated fatty acids, which could get together, making a clump, which could then clog the artery or the capillary. So saturated fatty acids are less heart healthy than an unsaturated fatty acid. All right, let's talk a little bit about simple lipids. We have a fat, which is also called a triglyceride, because it has three fatty acids hooked to a glycerol molecule. Let me blow this up. So when you combine a fatty acid to glycerol, an H comes off the glycerol and an OH group comes off the fatty acid. And you can combine three fatty acids to glycerol to make a triglyceride. Triglyceride is what we call a fat, just another name for a fat. And you can see this molecule if you simply look down at your belly. Everybody has fat in your belly. Everyone has at least even a layer of fat underneath the skin of the belly, even if you're very trim. And this combining of the fatty acid happens by dehydration synthesis again. So triglyceride is three fatty acids linked to glycerol. And I've already stated that the fat or the lipids are the body's richest energy source. They contain more energy per weight than any other molecule, meaning they have more calories per weight than any other molecule. We do store fats and lipids as adipose in animals. Any question about fats? If not, let's move on to phospholipids. They are another type of lipid. So we've talked about two. The fats or triglycerides, which are the most common fat in the body. But there's also phospholipid, which is also very common in the body because phospholipids make up the cell membrane. Phospholipids has two fatty acid tails, these blue purple things right here, and then a phosphate group attached to the third position of the glycerol, meaning this position 1 has the fatty acid attached, this position 2 has the fatty acid attached, and the third glycerol position we have a phosphate group attached. Why it's called a phospholipid. The tail portion, meaning the fatty acid portion of the molecule, is hydrophobic or nonpolar. And this portion of the molecule likes to associate or dissolve in lipids and fats. So if you put phospholipid molecules in a bottle of oil, they would dissolve in the oil because the um, fatty acid tails like being around lipids. Any question about any of that? All right, the other end of the molecule called the head is the region containing the glycerol molecule and the phosphate group. The phosphate group, and to a less extension, the glycerol. The glycerol here is not very polar. It's very slightly polar, but the phosphate is highly polar. In fact, you'll notice a charge on it. So it's actually got a charge or ionic molecule, is what makes the phospholipid hydrophilic. This region of the molecule, the head, is hydrophilic so that it can dissolve in water because of the head. That makes phospholipids a biphasic molecule. There are not too many molecules which are biphasic, being both hydrophobic and hydrophilic. One biphasic molecule that you're familiar with, or maybe two, is soaps and detergents. And the reason why we put detergent in our clothes when we wash them is because the detergent has a lipid portion and it gets into the oils in our clothes and then helps remove it. And then the other region of the detergent is water soluble and it gets into the clothes and washes it the same as water does. And that's why when we wash our clothes simply in water, adding no detergent, the clothes will not become as clean than when we add detergent. If we add detergent, we are cleaning the hydrophilic molecules out of the clothes as well as the hydrophobic. And if we're only cleaning it in water, we're only removing the hydrophilic molecules. We're leaving the hydrophobic molecules. So detergent is another molecule which is biphasic, and that is it can dissolve both in lipids or in something that's polar like water. And phospholipid is a biphasic molecule. Any question about any of that? All right. When we put phospholipid molecules together in water, they will start pairing up like this. And that's because the heads like to be near the water and the tails like to be away from the water. So they'll be on the inside. They like to be around other tails because they're nonpolar. They do not want to be on the outside because they are hydrophobic. And this happens in water where the molecule comes together like that. And then we'll even go further, start forming a lipid bilayer like this. And what does this look like to you? Anyone? What's that look like to you? All right. That should be obvious to you what it looks like. So I'm not going to state it because nobody's adding anything. So in water, phospholipids will come together to form this sort of a molecule where the heads are facing the outside, which is water, and then the heads are facing the inside, which are water, facing the water. And then the fatty acid tails come together on the inside, making the cell membrane a lipid bilayer. And that is the main molecule in our cell membrane, phospholipids, the main molecule in our cell membrane, making the membrane a lipid bilayer. And by the way, if you think about a blood cell in the blood is mostly water. The, the, the heads of the phospholipid will be on the outside to face the water. And then what's on the inside of a cell? Anyone? Anyone? Cytoplasm is what's on the inside of a cell. You should know that, by the way. And cytoplasm is mostly water, which is why the head is on the inside of this structure or the cell membrane, because the head will then be facing the water. Any question about any of this? Checking to see if anyone's actually here. Nobody's participating. All right, let's talk about steroids and sterols. They are the third type of a lipid. So we have fats and triglycerides, the first part type, and then we have phospholipids. Is that the second type? And then the third are steroids and sterols. Now, like the other biological molecules, most, or many, I should say, many lipids are made of monomers to make the polymer. And that was seen in the phospholipid, where we have a monomer, two monomers of fatty acid tails, and then one monomer of a phosphate group attached to the glycerol. So all of these are monomers of the phospholipid. And the triglyceride we have for the monomers, the glycerol, and then the fatty acid tails. But not all lipids have a monomer making up the polymer. And the steroids and the sterols are one molecule. They are not made up of smaller subunits. So with the lipids, not all of the molecules are made up of monomers. In the carbohydrates, all of the polymers are made up of a monomer. And that's true of nucleic acids too, and proteins, meaning the polymers of all of those other three biological molecules are made up of monomers. With the lipids, only some of the molecules are polymers, which are made up of monomers. And then the other molecules are like the steroids and the sterols. They are one molecule, they are not made up of monomers. A steroid is a four interconnected ring carbon structure shown here. If an OH group is attached to a steroid, we call it a sterol. The most commonly known and best known, most widely known, sterol is cholesterol. Cholesterol is made only in animals. So if you were to eat a diet based on plants, you will not get cholesterol in your diet. Cholesterol is only found and made in animals. One purpose we have for cholesterol is it's part of the cell membrane. I'm afraid I have to take a break here. Somebody's actually ringing my doorbell and I don't know why. So let's take a 2-minute break here. Can anyone tell me if we've had a 2 minutes now? I didn't look at the time before I broke.
It was about a minute.
Okay, so let's go another minute because I did tell people we'd be taking a 2 minute break.
Sounds good.
Okay, let's reassemble. Um, so cholesterol is only found in animals, and one place where it is found is in the cell membrane of animal cells. So we have more than just phospholipids in our cell membrane. Animals also put cholesterol in the cell membrane, and the cholesterol supports and adds strength to the cell membrane. If you remember, animal cells do not have a cell wall to help protect the cell. So animals put cholesterol in their cell membrane to give the lipid bilayer, the phospholipids, a little more strength. Any questions about any of that?
No questions, but it is 6:31, so I was wondering
Oh,
if
thank you.
we
Yeah,
needed to go to lab or not.
yeah, we should go to the lab. Anyway,
Okay.
I did finish this slide, so let me state, are there any questions? And if not, we're going to just stop and end here. Hopefully, I'm sharing my screen here. I don't know if I am or not.
You are.
Great. All right, I'll see you in the lab. Gosh,
Thank you.
Thank you.
start the lab at 6:35 because um, I want to give you a little break before we start the lab. All right?
Thank you.
All right.
Thank you.